At Consulting, I'm a reverse engineer, and I think I'm going to speak about heap corruption issues and how to exploit heap corruption issues to write to arbitrary memory locations. I had hoped I wouldn't be speaking that quickly. Never mind. Okay, so the speech will consist of two halves, and I'll start off with an introduction where I define what I understand is a first generation, a second generation, or a third generation exploit. I'll afterwards go a bit into heap structure exploitation. I'll cover some generalities on heap management. I'll speak a bit about how I go about understanding a heap manager, a closed source heap manager from the disassembly. I'll then go into detail on how to exploit a heap smash like a buffer overrun in a heap memory under Borland C, both regular smashes and off-by-ones. I'll then talk a bit about the Win2K heap manager and show one of the many ways you can exploit this one. Oh, yeah, I'll be demonstrating stuff as well. And then I'll be speaking a bit about the future of exploits because the landscape is changing a bit these days. And hopefully we'll take a break then. In the second half, I'll be speaking a little bit about format string bugs. I know most of you have probably heard about those, but as they fall into a similar category as heap issues, as they can write to arbitrary addresses and don't take control of the instruction pointer directly, I think it would be wise to cover them as well. And the end of the speech will basically be techniques to make NT exploits more reliable. I mean, we all know those things that you have to guess remote service pack, you have to guess what kind of OS is installed, if it's 2K, XP, whatever. So I used to work for a German pen testing company, and their pen testers were not very much into coding exploits. So they bought exploits off me, and I had to make sure that these exploits work under pretty much all conditions. I mean, it's an issue to get NT exploits reliable, so I'll be speaking about that. Any questions concerning the schedule? Anything I should add or explain more in depth right now? No? Good. Sorry, is there any water around?
Oh yeah, okay.
Thanks. Okay, we all know about first generation exploits, those regular stack smashers, this string copy, we've all heard about them. Well, just a short diagram to remind everybody how these things work. We have local variables of a C-style function in green. We have the frame pointer in white and the return address in red. And now somebody starts blindly copying data into one of the local variables and overrides both the frame pointer and the return address. When this function returns, it gets its return address it gets the return address, but that return address has been supplied by an attacker, so he can gain control. This is basically what I define as first generation exploits. They're simple stack smashes. They've been documented pretty much everywhere. Every little kiddie magazine has written about how to exploit a buffer overrun. They're pretty boring actually. And they exploit a hardware feature. They exploit the fact that the return value takes the stack pointer. Takes the return instruction takes the address at the stack pointer in order to jump back. So it's pretty low to the hardware when it comes to the level of abstraction where we're dealing. First generation exploits are usually when there's something like a string copy, it gets a sprintf. I mentioned before they're boring, and they can be detected via stress testing, as the application will segfault once the return address is overwritten. I mean, it will just jump somewhere like in some non-page space. There will be a page fault and an exception being raised. So you could find these bugs with stress testing, and I think it was Microsoft people who claimed that statistically speaking, stress testing would find most of them. That was supposed to be a joke. Anyways, they're almost extinct these days, as every kid was auditing everything. At least they're extinct in open source. You still find a few of those things or a few of these bugs in closed source, but even there they're getting rare because even the most backwards programmer has heard that string copy and gets might not be good ideas. Second generation exploits. Those were the exploits that came up when the string copies, gets, and sprintfs went rarer and rarer. They're basically, they come first off from the misuse of the so-called safe prototypes strn copy, strn cat. And they come from the fact that C array indexing starts at 0, so therefore addressing a 20-byte buffer at, index 20 is going to write out of the boundaries of the buffer. They're fairly well documented. There have been FRAC articles about them. And in contrast to the first generation exploits, they don't take control directly from EIP. And they don't even exploit the hardware feature itself, but they exploit something which was like convention in all compilers. It was the standard prologue and epilogue for all C functions. They can be quite hard to detect, especially in decoding loops like base 64 decoding, M code or MText decoding like Lotus Domino NVID. They can be quite hard to find. And therefore there are still a few of those around, even in major open source applications. When they actually get executed, or when such a buffer overrun actually occurs, we can get control by overwriting and manipulating the frame pointer. Now in this diagram, we have a target buffer in blue, to which we copy the data. We have the white frame pointer, and we have the red return address. So we start copying data into the target buffer and overwrite the lowest order byte of EBP. The function executes the regular C epilogue, moving EBP into ESP, which removes all the local variables from the stack, and then pops EBP, our manipulated EBP value, into the EBP register, and then issues a return. Now, we have to keep in mind here that EBP has been manipulated now. When the next function returns, we again have user supplied data in blue, the saved EBP in white, and the saved EIP in red. So the standard epilogue is executed again, which moves EBP into ESP. And what happens now is that the stack pointer slides upwards in memory because we overwrote the lowest order byte. So instead of pointing to the saved EBP and saved EIP, it slides upwards into the user supplied data. And then it returns, takes its return value from the user supplied data, and the attacker has gotten control again. Okay. I mentioned before that I have to consider format string bugs part of the third generation or of third generation exploits. They surfaced in summer 2000 by or through a WooFTPD exploit that got posted to BugTrack. I think the exploit was written by somebody called TF8. It's pretty much a new bug, or it used to be a new bug family. Nobody knew about it before, besides a few people in France, it seems, for a few years. They've had general keys to pretty much any computer in the world for a few years. So I'll get into the politics, what happened after format string bugs got public a bit later on. Anyways, these bugs come from a misuse of printf-style functions, where user-supplied data is given into the function as a format string. They're really trivial to spot, and by now they are widely exploited and well documented. They allow an attacker not to take control directly, but they allow reading and writing to arbitrary memory addresses. So in that aspect, they're similar to the malloc overflows, which we're going to cover next. Another thing is that they are not actually exploiting any hardware feature. They're exploiting something that is in the NZC standard, which apparently nobody bothered to read before. But it's not like we're dealing with something that cannot be changed. We could theoretically patch the libc and remove certain format characters, would just not be standards compliant anymore. So this bug species has been, well, hunted to extinction very quickly because they're very, very easy to spot, they're very powerful, and they're easy to exploit. So you have to, well, imagine it like a bug or any kind of animal you'd get a high market price for, and that's really stupid and will not run away when you look at it. So they're pretty much gone in open source. You can still find them in closed source. Not in all closed source anymore. Checkpoint fixed about 100 of them last year. Well, they're probably the only bug class there is that can be 100% automatically detected. So that might be one of the reasons why they are gone so quickly. Okay, heap structure exploits. Now, for a long time, everybody thought that a malloc buffer is not really dangerous when it gets overwritten, only if there is important data behind it. And a while ago, Solar Designer posted, I think it was a traceroute exploit to BugTrack, where he basically manipulated the heap management structures, the structures the heap implementation uses for managing memory chunks, and manipulated these to make the heap management function write to arbitrary addresses. So that spawned a whole new line of research into well, how to abuse heap implementations to write to arbitrary addresses. And these days it seems that the malloc-free exploits are more common than the standard stack smashes. Because in a lot of software, the standard stack smashing has been almost eliminated, while things like a double free, like one pointer which is free twice, or a heap overrun have gone unnoticed. It is on a way higher level of abstraction than either generation 1 or 2, similar to the format strings. And for Unix, it has been they have been documented in the recent FRAC by Max from Synergy. And the funny thing is, depending on your heap implementation, they are not or very hard to detect via stress testing. Because the data you overwrite the control structure with has to have a certain format in order to trigger anything. So if you just fuzz in there with with a bunch of A's, or you just send lots of X or whatever with a Perl script, chances are that you're dealing with a heap implementation that will not react to this kind of data. So there really is no way to reliably find these bugs without some sort of auditing beforehand, some sort of manual source code or binary analysis. Some generalities on heap management. Heap is that place where memory comes from if you do a malloc, and where it goes to when you do a free. That's all the programmer is supposed to know. There are a whole bunch of different memory management and heap management algorithms. I think it's like a standard computer science exercise to write your own. The Unix book book on Unix kernel internals by Ron Halja lists at least 8 different kernel level memory allocators. So you might have an idea of how many user mode allocators there are. Pretty much every compiler brings their own. Many compilers bring more than one implementation. A lot of applications actually have their own memory management in there in order to optimize performance. For example, it's actually recommended to do that. If you have an application which frequently allocates chunks of 20 bytes, you want to have a heap implementation that specializes in making those 20-byte allocations as quick as possible. So many large applications like Oracle, like Netscape Enterprise, bring their own heap implementation. And then there's the operating system, which might provide their own heap implementation as well as NT, 2K, and XP do. Every heap implementation requires a different way of exploitation. And every heap implementation requires a different data format to use in stress testing. So it's a lot of work, and it's pretty much, well, it creates jobs for people who like to read source code or binaries. Any questions so far? Okay. So we look at the Borland C Allocator. It is similar to something called Doug-Leah's malloc, which is the malloc implementation which is present in GNU libc. It is relatively simple in design. I'll show you a flow graph in order to make that more clear. It'll take a while, it's an evaluation version. Right. So this would be a binary flow diagram of the Borland heap implementation. Doesn't look all that simple right now, but if you compare it to Microsoft's heap implementation, it is really, really simple. Like less than a quarter of the size. So back to the slides. The exploitation of Borland C++ is very similar to the methods you use when you exploit a GNU libc overflow. And as most heap implementation, it mixes control structures with actual data in the allocated heap segments. For example, the FreeBSD or OpenBSD, I don't know, allocator doesn't store the control structures in the same place the memory is being taken from. So you don't have the mixing between allocated space, control structure, allocated space, but just allocated space, allocated space, allocated space, which makes it pretty much impossible to exploit these kind of things. So it would be considered one of the less secure, whatever, algorithms for heap implementation, for various reasons. So every memory block you allocate, for example with a malloc 20, gets a 4-byte control structure which is right in front of the block. So a programmer would malloc 20 bytes and he'd get a pointer right to this location back, and before that location there's 4 bytes which store some information about the memory block following it. And the heap would look similar to this once you've allocated two blocks sequentially. If block B is free, the control structure does not consist of only one double word, but of 3 double words. And whenever you now free memory block A, the heap allo or the heap implementation will try to defragment the heap by coalescing the 2 free buffers. It's very inefficient for a heap to have a lot of small free buffers anywhere on the heap. So most heap implementations attempt to have any kind of adjacent free buffers coalesced into one large buffer. So assuming we free memory block A right now, the 2 buffers get coalesced, and we have one large block with 3 double words as a control structure in front of them. So assuming we're overflowing memory block A, we want to basically create fake free chunks here, basically make the program, the heap implementation, think that the following block, the block after memory block A, is free. And then we want to create fake control structures here, so that when the heap implementation tries to coalesce these 2 blocks, writes to arbitrary locations. Oops. Let's look at the graph again. Okay, I've added some nifty colors. This is the same diagram as before. I've just colored the place where the actual coalescing happens in magenta, and the code path which leads to this place in yellow. So we'll now be reading a little bit of assembly language. This is standard function prologue, and arg0, the pointer to the memory which we are freeing, is loaded in EAX. Then the number 4 gets subtracted from EAX, and the value at that location is loaded into ECX. It's tested. We can't influence this value at all. It is in our diagram. Whoops. Where am I? In our diagram, that would be A data. So we can't take any influence on this, and therefore this branch will go down here where the other yellow box is. Some flag will be set, and it'll load the size. It'll load the size of this block out of this double word. It then adds it to a pointer to get the beginning of block B, of the next block. At this point, it checks whether the next block is free or not. You can see that in the graph right here. If the next block is free, it goes about and tries to coalesce the 2 buffers. We can safely ignore this piece of code, and here we are. EDX plus 8 is the beginning of the buffer B. The D word there gets being put in ECX plus 8, and ECX plus 8 gets loaded at EDX plus 4. I'm not sure whether I have it somewhere more visual, but we can demonstrate that in a few seconds. So basically, these 2 double words tell us what to do. Or we have to tell these double words where to write. We can see from the flow graph that the data with which we're overriding the beginning of B has to have this format. I'll explain why in a second. Well, these two things here, the two words at +4 and +8, are fairly obvious from this point here. EDX +4 gets loaded into ECX. To this location, the value in EDX +8 is being written. So basically, these are being exchanged and written to a certain location. And the format of this one is a bit tricky, but in order to even reach the code which we are dealing, we have to adhere to this format, because right here we have a certain flag being set, or a double word pointer EAX plus EDX +4 2. Now, if we do not make sure that this EAX plus EDX +4 points to a page location, we'll crash the program. So if we put the value to FFFFF1, it'll basically be a negative value, a very small negative value. It'll be subtracted and 4 will be added, so we're writing 3 bytes backwards in heap memory, which will still be paged. If you put any value here that is not large enough to make this semi-wraparound happen, you write to an unpaged location and just crash the program. All theory is gray. I think we'd better demonstrate this once. This is a small example program I'll use for exploitation. Doesn't do much, just overflows a malloc buffer and frees the buffers afterwards. I'll quickly load the executable up in IDA so we can have a better idea of what's going on. Okay, so we're dealing with test bcc.exe, and we'll run this program once, overflow the buffer a bit, and see what the program wants to tell us. Whoops, that was wrong. Never mind. Let's do it this way. I've pre-prepared this block here for overflowing. What we have here is A's, which will fill up the entire buffer A. And afterwards, F1, FF, 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 as I mentioned before. And then 2 values which are guaranteed to be paged, to which we can write arbitrary values. I'll just pipe this into our program. Now wait a second, we'll have to make sure the debugger will kick in. Okay, we're in the middle of the Borland Heap implementation. So we'll trace around a bit until we reach the part of the code we wanted to get to. This is the control block of A, which I mentioned before, which we cannot influence in any way. The flag is getting set, blah, blah, blah. You've all seen that. Okay, here we go. EDX, as we can see, is the data we have supplied, FFF1, FFF, blah, blah, blah. And the value at EDX +8, namely this value, gets loaded into register EBX. The value at EDX +4 gets loaded into register ECX. And now, we're writing the value at edx plus 8 into the location at edx plus 4. Up here. So basically by changing these locations we can write any value to any address as long as both the value and the address are paged in memory. Does everybody believe that, or should I demonstrate that we can change the numbers and things will still work? Okay, I should be changing the numbers. Somebody tell me a number. 8 digits, please. Okay, well, we'll come up with something. That should do it. Of course we'll get a seg fault now, but okay. EBX is being loaded with bad code spelled backwards. ECX is getting loaded with the other value we supplied. And if we wonder why these values are all changed around, that's due to endianness in the file versus endianness in memory. And then they write to ECX plus 8, which is non-page, which will trigger an exception, and the program dies. Any questions concerning this? Yes?
So what's the purpose of the original malloc to write that memory?
The question is why the original free is writing to that memory.
Yeah.
Basically, they're trying to coalesce the two blocks, like the two free blocks, and then moving pointers around.
Like what is the what pointer is at the original location of a free block?
Excuse me?
What you know how when you free a block?
Yeah.
Three D words.
Yeah.
That they're allocated.
Yeah.
What is the structure that holds? What are those pointers in those D words that are supposed to be pointing back to memory, like a linked list? Holding or something?
They usually point to a table of free blocks. So they are supposed to enter themselves into this free table. I haven't really investigated what Borland C does exactly at this point. I don't really look much further than where to exploit it. On the other hand, yeah, it's usually used for coalescing of blocks or for putting a free block into some kind of linked list or some kind of table. Any other questions concerning this? All right, then we'll be moving on. Okay, so we're lucky with Borland C++. In contrast to Windows 2K, we can exploit off-by-ones in heap memory. We'll have a look at the code in a second. Never go out partying with Microsoft people. Seriously not. Okay. I have another graph for this. Okay, now assuming we're exploiting an off-by-one, I mentioned before that we can't really reach this byte before us, the control block of A. What can happen though is that not our buffer which we overflowed gets freed first, but the buffer into which we overwrote, or into which we, well, overwrote by 1 byte accidentally. So what happens here is that the lowest byte of this double word which is being checked is set to 0. So we had this part in the graph before, and at that time we couldn't influence this particular check here. So now we're overriding this location with a 0 byte. So this test here, instead of taking this branch down here, is going over here. And we can see that we can reach the same magenta code block via this route as if we had gone through this here and land it in a different magenta block. Wait a second. I'll compare the two for a second. So there's one overflow, or not one overflow, one arbitrary memory override happening in this block and one here. And the route we just took was this one. And the route we can now take with the off-by-one is this one. So we're basically setting the next block's lowest order byte of the control double word to 0. We can pretty much safely ignore this entire block over here. And then we land at the typical pointer exchange again. Same game, same layout, and there really isn't much different here this time, just that we have to control the next buffer, meaning we have to control not only this buffer, which we overrun, but we have to control the contents of this buffer as well. Because what we're doing right now is we're making the free belief that he should be taking 3 control blocks from here, which obviously are not there if we can't control that buffer. So we need to control both this buffer, which we overrun, and the buffer into which we overrun by 1 byte. I'll have a demonstration for that as well. Another small program, which this time gets 2 buffers, which we could control and freeze them consecutively. And something which will first overflow the first buffer with an off-by-one, and which will then put these 3 double words followed by ODOA, new line, into the following buffer. Okay, so we're tracing down a bit. This is the branch that we normally could not be influencing, but which we are now taking. Some flag is being set. We want to ignore all this crap. And here we are. Classic pointer exchange. The 3 double words. And we're overriding arbitrary locations. Any questions?
If the freeze were reversed, would you just reverse the data from the two gets?
If the freeze were reversed, well, why would I be reversing the? Well, why?
In the code, if it was,
yes.
it was free data 2, then free data. So the code you showed it was free data 2, then free data 1.
Yes.
If it was free data 1, then free data 2, would you reverse where you're putting the data for the gets?
No, because I can't really reverse that, because I'm. Sorry?
It wouldn't be exploitable in that case? Or?
To be honest, I haven't tried. Should I try?
Sure.
All right.
Afterwards, fine.
But let me think for a second. To be honest, as the actual pointer override happens not in the free of. Oh, wait a second. We'll just check it.
It happens in the second free, right?
No, it happens in the first free. So as this happens anyways in the free of this buffer, freeing this buffer first should not have any impact. But should have and does not have are 2 very, very different things. So we'll just try that. Okay. Whoops. I should compile it first. Yes, good. Okay. Right now we don't have a breakpoint on the allocator, so we gotta load this file in IDA and set a breakpoint on the allocation function. It'll take a minute. It'll take a time. There you go. So this is the small memory allocator. And that's at 401C04. We'll quickly patch, We'll quickly patch a breakpoint at that location. And try it out. So this is the first free, which should not do anything, so we'll just forget it. This is the second free. Which it seems to go somewhere completely different. I'm a bit lost right now, wait a second. Oh, this is called a bit too often, something is going wrong.
Wouldn't you need to reverse the data?
Well, I'm not quite sure because, to be honest, I'll try that later and we'll see then. Because mainly it shouldn't make any difference because we're manipulating this point and the data is still in here. And we're overflowing this buffer anyway, so reverting the data would not really, at least in theory, should not do any or be anything different. But then again, theory is theory. Let's move on to Win32 heap management. This is a nice diagram I came up with one day. Basically, when you're dealing with Win32 heap management, you have a lot of different possibilities with which malloc implementation you are dealing. There could be a customized heap implementation that the application has provided itself in order to enhance performance. Could be the regular libc which is provided with every compiler, like the Borland libc or the Visual C libc malloc. Or it could be the direct way to the NT heap memory API via heap alloc, heap free, and so on. And what's funny though is that all three allocation functions in the Win32 API, local alloc, heap alloc, and global alloc, end up calling RTL allocate heap and NTDLL. I heard that these two are only there for legacy reasons, so that might be an explanation. So what we need to do is take apart RTL allocate heap in order to find out what we have to do in order to write to arbitrary addresses. Well, the entire RTL allocator is not documented by Microsoft, at least not publicly available. It seems to change from time to time. At least I've seen NT builds which had a different allocator than my 2K build has. And it is considerably more complex than Borland's algorithm. I'll quickly show a small graph. So this is the simple free in RTL free, but it calls a bunch of subfunctions which are not really to be called simple. This is the Win2K heap implementation function, which is there for coalescing free blocks. Normally people would laugh at this point. Come on. Is everybody that tired? Didn't see any of you singing karaoke yesterday. Okay, that's an excuse. All right, there's two different ways of exploitation of buffer overruns in the Win2K heap manager. I'll just cover one. The other one is for exercise at home. So, in the Win2K environment, you have an 8-block control block before every memory block. So, after two allocations of 32 bytes, we again have those two adjacent blocks with control blocks in between the two. And when we're now overriding control block B, we can play a few funny games. Where we? Right here. So I've highlighted in magenta again the two overrides which we want to get to, or we only want to get to one, which is over here. This one. So I'll quickly highlight the code path we have to take. I should get the full version of this program soon.
This is licensed to.
Sorry?
This is licensed to.
Well, must be a mistake. Happens sometimes. Okay. So this is the path we want to take. Going all the way through all the yellow boxes and landing down here. So we'll have to read a little bit of assembly again. Standard prologue, more or less, setting a few variables to 0 and so on, testing whether this is the pointer being passed into the free is not 0. Whoops, I shouldn't buy this program. Just crashed. Didn't do that in rehearsal though. Okay. So we have the standard prologue. We're following the graph. It's not really interesting to us right now. Here we see that the control block address, is being loaded into ESI. And then the bit 1 of the byte at ESI plus 5 is being tested. In order to get to the code we want to reach, it has to be set. So we know that the data with which we're overflowing the buffer has to have the bit 1 of the 5th byte set. This is just well, this is not an important check. You just have to make sure that these 3 bits are not set. Otherwise it'll report an error and not get to where we want to go. And whoops. Oh no. Okay. Then we'll do it a bit less visual. So this is the disassembly. Quite lost though, I need that graph, damn it. Okay. We've been here before. We've been here before. Here we are. Field 4, the byte at ESI plus 4 has to be smaller than 40 hex in order to reach our code. So 40 hex is like 1 below the A. So if you stress test the heap implementation with A's or B's or any kind of letter, you will not reach the relevant code. So just sending large strings will not help. Okay. This is not really interesting, blah, blah, blah. And we end up at this point here, where the byte at ESI plus 5 is tested against having bit 4 set. If that bit is 0, we're getting to where we want to go. So from this graph, we can see that the criteria for the block which we have to write are: bit 0 of flags have to be set. Flags is the byte at ESI plus 5. Bit 3 of flags must be set. Field 4 must be smaller than 40. And the first field, own size, must be larger than 80. I'm not sure where we had that larger than 80, but it has to be that way. So the block XXX 99XX meets all the requirements. And if we actually overflow using that block, or with that block, we end up at this point, at ESI minus 24, and then we have the pointer exchange. So ESI was before pointing to the block B control data, and then slides backwards into the memory area which we control. Remember, we're currently freeing memory block B, we're not freeing memory block A. It slides back into memory block A to this location, and then it loads the double word at that location, saves it into a local variable, loads the double word at that location plus 4, saves it into a local variable, and then does the traditional pointer exchange. So we can have a quick demonstration of how this works as well. Okay. This should be 20, 30, 32. Okay. Obviously we do have a seg fault. Would be nice if I could show how we got there though. So okay, we're going to set a breakpoint on this location here, 412A5. Um, 2A5? Was that what I said? Okay. Oh yeah. Okay. Here's our breakpoint. We trace into RTL free heap. ESI plus 5. The flags byte is tested. Does anybody happen to have a paper tissue? My nose seems to be running. We're entering a critical section. There's a new word I learned 2 days ago. It's called mooch. Thanks. I'll switch the microphone off. Damn it. No, I do have enough stuff to present. I'm not trying to waste time. Okay. Back to work. All right, we just entered a critical section. And here we are. Add ESI minus 18 hex, which is 24. Save it into a local variable. Load EAX with a double word at that location. Look what's in EAX right now. The stuff we supplied down here. All those letters that we typed before. It's being saved in a local variable. ESI gets loaded with a double word at ESI plus 4. So ESI has been supplied by us as well. And then they try to write this value to the location at ESI, right here, and to write ESI to the location at EAX plus 4 right below. So again, we can write any value to any location as long as both values are paged. And we now get a nice segfault. Any questions? No? All right. Okay. So things to note down for the Win2K heap manager. If we can overwrite at least the lowest 6 bytes of the next control block, we can have the pointer slide backwards for 24 bytes in the middle of our buffer and then write to arbitrary addresses. Secondly, it's quite important to know that there is way more than one way to exploit these. You've seen how large the entire RTL-free heap and the coalescing is. I do have a complete decompiler of the RTL-free heap, but I haven't bothered to decompile that coalescing function yet because it's so ugly. So there are many more ways to do this. Really depends on your situation. Take a disassembler, take a debugger, take a few days. And well, good luck. Okay, so to sum up the first half, or to begin with summing up the first half, things are changing these days, especially the way bugs are being exploited and the kind of bugs that are being discovered change. The standard stack smashes are slowly going away. And what is more prominent these days are heap-based overflows, double freeze, format string bugs in closed source applications, and I think that the standard how to exploit a string copy is not going to be very relevant in the future, especially with Microsoft finally introducing something kind of like StackGuard for Visual C. The standard EIP overriding on the stack will not be there anymore, which doesn't bother because it's boring anyways. Right? Well, you can see biological analogies in the world of bugs, that valuable and easy to find bugs are not going to last long. So we've seen with format string bugs that a particularly easy to spot bug, which is very powerful, will be very, very, very quickly gone. And some people have realized over this entire format string thing that bugs are something like a natural resource. And that's basically where most of the push these days from the hacking community to not publish anything anymore comes from, because some people have realized, damn, we might be running out of bugs at some point. So it's quite funny, because on the one hand you have people like Microsoft and this entire alliance of security companies saying, well, we want responsibility disclosure and so on. And on the other side you have the hackers, or lots of the hackers, saying, hey, we're not going to publish anything anymore anyways. So we really have a bit of a paradigm shift here that I think the future is heading towards administrators who get owned with 0 day. And that is every administrator's nightmare. So secondly, the bugs are changing as the language is changing. As more and more programmers use C++, OOP, STL, whatever to write their code, we will not have those, or we don't really have those string copy overflows anymore because everybody's using string classes. But a lot of those pitfalls in those languages haven't been really discovered yet. It took us 15 years to find format string bugs in C. So who knows what's there hiding somewhere in Java or somewhere else. Especially with STL, off-by-ones are possible. I mean, everybody knows that, or anybody who has programmed with STL knows how annoying it can be to use an iterator which is not valid anymore or similar things. So you can mess up C++ code quite badly as well. Well, the new bugs which are currently coming out are mostly heap overruns. And due to their nature, they are not being found via stress testing anymore. Or, well, not many of them anyways. So pretty much we can kiss Perl goodbye, all those million Perl scripts that we've written to fuzz every server there is. We don't really need things like Retina anymore with its advanced II that's built into Perl. And well, fuzzing will not do it in the long run. We need people to read the code. Actually, I think we have to get away from the idea that it is possible to remove bugs automatically in any way. Bugs can only be removed by a human because any solution of, or even identifying a logic bug in the implementation of anything is equivalent to the halting problem and is not solvable automatically. So don't think bug finding can be automated. Some parts can be, but nothing will prevent you from having to read the stuff. Reverse engineers are, well, have a bit of an advantage when it comes to closed source applications because they're the ones that can document and analyze the heap implementations. As somebody who doesn't know assembly language, you're going to have a hard time finding out what exactly is going on or how to even exploit a heap overrun. With a stack smash, it's fairly easy. You just smash the stack, point the pointer somewhere, take somebody else's shellcode, put it in there, and hope that it'll work. With heap overruns, especially in a closed source environment, you need to analyze the heap implementation yourself. There's just no way around it. Well, whether you're sure if your Java runtime is working 100% correctly, I will not even ask that. Then we have to know that library functions are increasingly, or not increasingly, but they're being discovered as being a major source for bugs. And many compilers have buggy library functions. For example, Borland C has a buggy malloc. And well, if you run statistics over source code, I don't think you'll find any library call that's used more frequently than malloc. Anybody spot the mistake? Mistake is defined as anything that would malloc behave in a way that it's not supposed to behave. A line size is furthermore used.
Never check for negative.
Sorry?
Never checks for negative size.
Right. Exactly. So if you put something in there like request a size of -1 or 4 gigabytes, wrap around down here and allocate something like 8 bytes and or 9 bytes and mess the heap up during that process. So any kind of malloc which takes a user influence value is dangerous. And there's a lot of mallocs which take user influence values. For example, if you try to allocate an array of structures and the user puts something in there like user supplied value times size of structure, which would allocate an array. If that wraps around or even gets to 4 gigabytes and the program thinks everything's fine because malloc didn't fail, but returned a pointer to a 12-byte buffer, things are going to get screwed somehow. And some people claim that major bugs are, or the major bugs are slowly going out of the open source projects as well. This is an allocator from a major open source application, and that one is buggy as well. Those people who were in my class know this one already, so they're excluded from answering this. Anybody else know the mistake? Let me think. Well, what do you mean by it doesn't check size?
It does new block with size.
Yes?
But it checks.
it checks request size for negative value, but it doesn't check size for negative value.
Yes.
So if rec size is what value would it be? She gave, I think, some small value of rec size generated a negative value.
Not exactly, but you're close to it actually. The logic bug is basically that they check size, check rec size, but use size. What happens here is they round the request size up to the next align value. So, and rec size is an int, a signed int. And signed ints become negative as soon as the highest level bit is being set. So if you send something in there which is like right below 2 gigabytes, it'll round like right a very large positive number which is very close to being negative, which will wrap around to be negative if you add 2 or 3. This rounding up will wrap around to be negative, and this check will pass because you put a positive value in there. And this call will corrupt the heap. And as long as we find bugs like these in calls which are that frequently used as malloc, I don't really think that any one of us is going to be out of a job soon. Anyways, I think it's time, well, not exactly yet, but I think it's time to have a break. Thank you.